Welcome to pattern analysis. Today we have our third clustering method, the mean shift algorithm, and we're going to talk about hyperparameters for clustering. If we check here, I put the paper up in StudOn so you can have a look, like a first-hand look by yourself, but of course we also walk through it here. The idea of mean shift is that it says, well, all these samples, they should represent a density, or I can look at the samples in the space as a density, and then I can perform a gradient ascent on that density and converge to a mode, a local maximum of that density without actually estimating the full density. I just look at the gradient, like how do I get to a mode? And then if I start from every sample and walk towards its local mode, then we end up in a situation where this sample walks up here, that sample walks up here, this sample walks up there, that sample walks up there. And in a post-processing step, then we can collect all samples that are up here and can say, okay, these belong to the same cluster. We can collect all samples that walked up there and we can say, they also belong to the same cluster. So this is the idea. But first of all, we look at the math behind it. And if you think about the representation that mean shift kind of implies, then you can say it's like having a middle way between the k-means algorithm and the Gaussian mixture models, in the sense that k-mean clusters minimize the distances between samples. Yeah, I mean, also we said both k-means and GMM clusters both have these responsibilities, so but let's assume this view here. K-means clusters result from minimizing distances between samples. GMM clusters result from a full density estimation, you could say, a parametric density estimation. And the mean shift clusters, they have a few local kernel density estimates as a gradient ascent step. Let's have a look at the math. So we want to do a gradient ascent on that density. As the underlying vehicle, we use a kernel density estimation. Our Parsons window estimator will come into play here. And we make a constraint. So we say we are only looking at radially symmetric kernels. What does radially symmetric kernel mean? So the kernel function only depends on the Euclidean distance to a sample. So bam, here it is. We have a Euclidean distance x0 minus x squared Euclidean distance, sorry. And if this is the only thing that is relevant for calculating or for evaluating the kernel function, then we can rewrite the kernel function, which usually is a two-parameter function, x0 and x, to a one-parameter function, lowercase k in that case, times some constant, doesn't really matter. And k of x has a separate name. If you check the paper, the mean shift paper, you'll find it there also. They call it the kernel profile. I'm not 100% sure, I didn't check whether this also finds applications anywhere else, but if only the distance plays a role for evaluating the kernel function, then you can already think about it like a sphere, a function that has a clear, like, d-dimensional sphere underlying in some sense, and only the distance comes into play, so the name profile kind of makes sense, I would argue. If we think about what can we express with such kernel profiles, well, we can, for example, encode a Gaussian kernel by saying, well, we take that Euclidean distance and put it into the exponent of an e. So e raised to the power of minus 1/2 of x would be a Gaussian with a standard deviation of 1. No? What will also be super important for the purpose of mean shift is the Epernetchnikov kernel, because this actually allows the mean calculation. So the name mean shift comes from the evaluation of the Epernetchnikov kernel. Let's have a look at its definition. So Epernetchnikov kernel, if we feed the profile to it, the kernel function, super simple, is just 1 minus x, as long as x is, or the magnitude of x is between 0 and 1, and 0 otherwise. So you may already wonder, like, okay, a Gaussian with standard deviation 1, an Epernetchnikov kernel where this has to be between 1. This is, I took the definitions from the paper, but where this comes from is that the authors are implicitly assuming that the window size, the kernel size, has been part of the calculation of these squared differences. So actually what we are feeding is something like x0 minus x divided by some window size h. Yeah? So the size normalization already took place. Here, I think we just have to keep this in mind, no? That we can scale the input to such a kernel function. Okay, so with these definitions, let's have a look at the density estimate and let's calculate the gradient there. You know? So we have a density estimate P of x, let's say, and we are interested in the gradient of that density at position x. So P of x, we can expand this. It's just a normal standard Parsons window estimator with some kernel. The kernel has parameters lambda. Here comes the gradient. Because of linearity of the gradient, we can put the gradient inside of the sum. And we can replace the kernel function now with our assumption that we are operating on kernel profiles. So only the distance between x0 and x plays a role. And just for brevity, let's rewrite that distance as s. And then we can calculate the first derivative of that kernel profile with respect to x. So if we take the derivative of the kernel profile with respect to s, then we need the derivative of the kernel profile of s, but we have to also apply the chain rule. So s derived with respect to s is just that squared function, our Euclidean squared function derived for s, and this is minus 2 times xi minus x. Okay, now we can put this together and say the derivative of that density P of x at location x is 1 divided by n, the sum over all samples. This is just our standard Parsons window estimator. We multiply by our constant c. This also doesn't change the world. But here we have the derivative of our kernel profile times, now chain rule applied, minus 2 times xi minus x. Yeah? So this is the gradient at position x. And in order to get to a maximum, we have to set it equal to 0. Now let's do the calculation. This is just a copy of the equation from the previous slide. First, let's drop the c, so we can divide by c, it's just a constant. Let's also drop the 2, we can just divide by 2 globally, it's also just a constant. And then let's multiply out the xi minus x term, so we have the xi here and the x there. And let's rearrange everything such that x is isolated. So this gives us an expression of our, like we go over all samples 1 to n, we take the derivative of the kernel with our squared Euclidean distance as input multiplied by observation xi and divided by these derivatives of the kernel, like calculated for all samples, minus x, so the location where we evaluated, equals 0. This is an important equation. This is called, so the last row is the normalized gradient, and it's called the mean shift vector. Okay. Now, how can we use that mean shift vector? The mean shift algorithm essentially consists of repeated calculation of that mean shift vector. So here are the 3 steps. So first, calculate the mean shift vector m in iteration t. Okay, so this means we look at location x, we calculate exactly what we derived on the last slide and calculate and subtract the position for that we're looking at in iteration t. And then we do a position update. So the next position is the current position plus the mean shift vector, which implies if we have here the current position and for the calculation of the mean shift vector we subtract the current position, effectively the update, the new position is literally just the evaluation of that normalized gradient at the current position xt. Yeah? Okay, great. And this is repeated until convergence. So that's all. So this, we repeat this, repeat. So we do the gradient ascent until we reach the location where the gradient is flat, so where there's no further possibility to go up the gradient. And then we say, okay, probably we reached our position. So if we imagine this, we move. Okay, and here it's flat. The gradient is flat, so no further update here. No? This is the gradient here. If we reach the maximum, there's 0 update, so we stop. So, and to plug this together to a clustering algorithm, you can say, okay, easy. I just run mean shift for each of my samples. They all will converge to some point. Not the very same point, but nearby locations. And then I need a second processing step that says, okay, like I do some post-processing that groups together samples that converge to nearby locations. Yeah? So if I have multiple samples that essentially are at the same location, then I can merge them into one cluster. Okay. So the parameters that we need essentially are only the parameters for the kernel. So window size for Epernetchnikov or Gauss kernel, so this scaling parameter. No? And then whatever we need for the post-processing. So I call them cluster linking parameters here. This, of course, is also something that needs to be done. But we're not going to discuss this a lot. Okay. So in tendency, the same rules of thumb apply as for the density estimation. If we think about larger kernels, and we're going to look at examples in a minute, larger kernels will lead to less clusters, less local maxima. Smaller kernels will lead to more clusters, more local maxima. And just as a general comment, the shape of the mean shift clusters, it can potentially be less regular than the shape of GMM or k-means clusters, and we're going to talk about this more in our meetings. Yeah. So what is the role of the Epernetchnikov kernel? So with the Epernetchnikov kernel, the update is just the mean of the samples within a d-dimensional sphere. And this is why the algorithm is called mean shift. And this is what people are using also in practice. No? And similarly, as we discussed it for the k-means, no? The Euclidean distance is sensitive to scaling differences. So you need to normalize your input dimensions. Okay, we talked about this. If you have the feeling we should talk more about it, then please reach out during our meetings. Okay, let's look at a practical example. So here's our distribution of points, the same distribution that we used already for the k-means and the Gaussian mixture models. So what I show here is the sample of interest. Here I'm using the Epernetchnikov kernel, so this is the window of influence within which we are calculating the mean update. And and iteratively we go through that. So let's have a look. So we are at this location. We have a couple of blue samples here in our area of influence, and they are all on the right. So the higher density can be expected to be on the right, and our kernel is going to move, or our sample position is going to move in that direction. So it moves over there, and now so it moves over there, and evaluating the kernel from that location leads to an even higher density, or even more samples here in that domain. So we're going to move further in that direction. Now, evaluating the gradient of that density in that location. Now we have a little bit here on the left. We have more on the right. So probably we move further right. It's like a little bit, no? Let's check again. Now nothing changed anymore. This point converged to this location. Yeah? Now let's pick another sample. It happens to be over there. And just looking visually at this disk. So here are the observations. The density will be higher in that direction. So we will see an update in that direction. Yes. Okay, now we're here. Again, the density seems to be higher, so in this direction. So we will likely see an update in that direction. Yes. Let's see. Will we have another update? Yes, a small one. Will we have another update? Very small one. And now we converged. So let's pick a third sample. So it jumps over there. It jumps over there, it jumps over there, jumps over there. Will it ever stop? Maybe here. Okay. Now we moved. And if I'm iterating this for every point, then we get the result that we're seeing here. So what we see is in this upper part here, all these samples that converged there, they were really closely nearby. For the other two clusters, so we would obtain 3 clusters with the post-processing, but for the other 2 clusters, it's not so unique, no? So you see there's a little bit of a distance here between these samples. So depending on how you configure the post-processing, they will be collected together or not. No? Okay, into individual clusters. And this, of course, changes with the kernel size. So let's have a look at an output for a kernel size of 1 first. This is the output for a kernel size of 1. And what we're seeing here is that a smaller kernel leads to more clusters by tendency, because we have a smaller area of influence, so we more easily settle to local modes of that density. And very specifically, let's check through it. So here most of the points in that upper cluster still meet in this one location here. One went a bit stray. Okay, I don't know. These two also are kind of disconnected from the rest, so they will maybe form their own cluster. Here also is some like partial disconnect happening. Whether this will be 2 clusters, 3 clusters, 1 cluster, depends a bit on the post-processing. They are fairly compactly together still, and they also got a bit disconnected from the rest, will probably be a separate cluster. Let's have a look at a larger kernel size. So here's a kernel size of 2. So for a larger kernel, clusters start to merge. Yeah? So we have a larger area of influence, so more remote locations are summarized together. So this was compact already, it's still compact. This is another group. But here what we're seeing is they are kind of lining up. It looks as if this will be one cluster. And if we further increase the kernel size to 2.5, what we see then is that this is converging to a single cluster here. And here we have a second cluster down there. If just out of curiosity, if we further crank up the kernel size to 3, then everything meets in one cluster, which kind of makes sense. So the kernel size is our, let's say, setting for the granularity with which we want to look at the data, to subdivide the data. Okay. We can talk more about the mean shift clustering in our joint meeting on Monday and on Thursday. Now let's talk about the hyperparameter selection for clustering. So how can we choose the hyperparameters for clustering? For example, the K for K-means and the Gaussian mixture model clustering, or the bandwidth, the kernel size for mean shift. Clustering algorithms, and in particular the 3 that we looked at, they are unsupervised. So we cannot just say, do some cross-validation or whatever, align this with labeled data. This is not how unsupervised learning works. So we require some special ideas for the hyperparameter selection. And in this lecture, we will particularly look at the gap statistics as a particular method for k-means. The reference for that is the book by Hasty, Tibshirani, and Friedman, section 14.3.11. Then I'm going to briefly touch the hyperparameter selection for mean shift. And then I will briefly talk about the Gaussian mixture model hyperparameter selection, but we will not carry it out today because we need more methodology for this. So it's kind of a motivation then for the next topics in the lecture. Okay, let's begin. So gap statistics for k-means. What is the idea of the gap statistics? So we briefly mentioned, maybe you recall that one application of k-means is vector quantization. So, and you can say, what is vector quantization? It's a task of encoding a distribution of points with a few distinct vectors. And then you can start to ask questions. No? Okay, if I'm encoding a distribution of points with a few distinct vectors, how can I measure the quality of that encoding? And you can say, yeah, well, let's have a closer look at the within cluster distance. We can use this as a measure for the encoding error. So any distance between the points, or in particular the sum of distances of all the actual observations from their prototypes, can be seen as encoding error. And if we now say, well, our goal is actually to do hyperparameter selection, so to choose the k, then we could rephrase this question as the optimal number of our vector quantizers. And what would be the optimal number of the vector quantizers? So we can say, well, it needs to be large enough to achieve an effective encoding of the given data, so with a low within cluster distance. But in particular, also we want to have a small k, a k that is as small as possible, because otherwise it's a trivial task. We can just say every data point ends up in its own cluster, but this, of course, is a bit pointless. So the gap statistics defines this task as follows. It says, let's choose the smallest k for which the difference in the within cluster distances between a clustering of a uniform distribution, so maximum chaos, you could say, and the given data, which should have some structure, is substantially better than if I would be using one vector quantizer more. Yeah? And we're going to talk more about this. Okay, so let's start with the within cluster distance. So we have the differences of each point that is assigned to a cluster to its cluster center squared, multiplied by the number of points in that cluster. So CE cluster number for sample xi, and k the total number of points in cluster k, and mu k the mean of all points in cluster k. Also recall that the within cluster distance is a quite natural choice to optimize for compact clusters. Yeah, so that is the motivation, and we're now going to use it with the gap statistics for selecting the optimal k. Okay, so what happens if we change the number k for a clustering? Yeah, just for demonstration, I just drew a couple of points from a couple of Gaussians here with overlap. Yeah, and here on that side, I plotted the log of the within cluster distance on the y-axis and the number of clusters that have been used on the x-axis. So we start with one, like putting everything in one single cluster, then into 2 clusters, 3 clusters, and 20 clusters. If these are, I forgot, if these are 60 points or something, then for 60 clusters, of course, the within cluster distance will be 0. But I didn't go that far. What we see as a general observation, and this must be like that, is that the within cluster distance decreases. Yeah. Because the more clusters we have, the smaller the distance on average to your next cluster center. Totally makes sense. Okay. Now, people started to use this directly for model selection. Yeah? But it's not a super great method. But let me mention it for the sake of completeness. No? So we said for increasing k, the within cluster distance decreases. So if k equals the number of samples, then the within cluster distance is 0. So this we can say is a trivial solution. But this implies that we cannot just do what we did for other tasks, that we say, okay, let's calculate the derivative, let's set it equal to 0 or something like this. This will not work. Yeah? Another thing that will not work is the so-called elbow method. So elbow method means, well, let's look at a location where we have a decent decrease in the within cluster distance before that, and then like diminishing returns afterwards. And this then supposedly shall be the elbow. So if we check how many clusters were these, 5 clusters, perfect, this is my clustering number. This may work in some extreme cases, but in practice it's just a problem because it's not really clear which of these little edges there is a significant bend, yeah, in the progress of that within cluster distance for increasing numbers of clusters. No? Like if I look at this curve in particular, like, I don't know, at 3, at 4, at 7, this might all be plausible solutions. And the gap statistics by Hasty, Tipshirani, and Friedman aims to solve this problem. You know? So the idea is to create an artificial reference for the within cluster distance and say, okay, for that reference, I use samples that are drawn from a uniform distribution. And why a uniform distribution? A uniform distribution is something where actually I cannot learn anything from that structure. It's a distribution with the least possible structure, so there's no potential for compressing anything if I see the vector quantization as an encoding problem. And then I can relate the within cluster distances from that uniform distribution with the within cluster distances that I obtain on my actual data. Yeah? So let's have a look at the algorithm really quickly and then we can discuss it a bit more. So first step. So let's draw some uniformly distributed samples. And just for statistical robustness, not just one set, but let's take B sets, 20. In Tipshirani's work, it's 20 of such data sets. Let's use each data set individually and let's calculate these curves with these within cluster distances as what we looked at, like for different k, let's calculate the log of the within cluster distances, and let's average them. Yeah, and this shall be this log of the on the uniformly distributed data. Okay, and then let's relate this to the within cluster distance of our for k clusters on our actual data. Yeah? So for k clusters, calculate the gap g of k, and this gap shall be the difference between the reference log of the within cluster distance on the uniformly distributed cluster and our log within cluster distances on our data. Yeah? And the criterion for selecting the optimum k is to choose the smallest k for which the gap, so the difference between the within cluster distance of our reference data and the uniformly distributed data, is larger for k than for k plus 1 minus some standard deviation of these 20 draws that we had for the uniformly distributed data. Yeah. Okay, so let's have a look at some example output. So here I drew in gray these like 20 log reference curves from samples drawn from uniform distributions. The red line in the middle here is effectively the mean. So the mean log uniform within cluster distance. And orange, this is what we obtain on our data. Why is the within cluster distance of our data lower than the within cluster distance on the uniform distribution? Well, because our data has structure. We can discuss this a bit more in our meeting, yeah. But any structure in the data helps to reduce the within cluster distance. So conversely, we can say the within cluster distances on the uniform data, they have to be an upper bound, like an empirical upper bound, you could say, on the within cluster distance of our data. And this is also the idea that comes into play when we now look at the gap. So the gap is the difference here for one particular k. It's the difference between the uniform reference distribution here and our distribution. So and if that difference is particularly large for 1k, particularly considering the k plus 1 value following afterwards, then we say, okay, we take that k, it already isolates enough structure in our data, so we pick that. Yeah? Okay, so this is the idea. Okay, let's briefly read through this. The orange curve, so recall that the reference curve has the least possible structure. It's a uniform distribution. Hence, the orange curve can be expected to be lower than the gray curves. Think about Huffman codes. Foreseeable events allow more efficient encodings. Yeah, it's one way to look at it. Uniform distributions imply that samples can appear anywhere with identical likelihood. So it will be the perfect surprise in a way. Okay, so and conversely, if samples are somehow clustered together, they are more likely to be closer to cluster centers So we are less surprised about the occurrence in that line of thought, and we get a lower log within cluster distance. Okay. Here's a different way of drawing this. So this is a plot that directly plots the gap. Yeah? So here on the y-axis we have the difference of the uniform, the within cluster distance of the uniform distribution minus the within cluster distance of on our data. Yeah? And we see here for increasing numbers of clusters, so from 1, 2, 3, this difference increases, which means that we are exploiting more and more structure in the data. Yeah? And now our selection criterion is let's check the difference that we have for k. Here k equals 3. This will be the value that will be selected in a second. Yeah? Let's compare this to the difference for k equals 4 and minus a standard deviation. And it turns out that for k equals 4, we have like diminishing returns, you could say. Like adding this additional cluster, k equals 4, doesn't bring us more gains in this gap. So therefore we say, okay, it's fine. Then let's stick to k equals 3, and this is going to be our solution. Yeah? Okay. So yeah, now we could say, well, why the first gap? Yeah, because there are other situations. If we look at k equals 7, there's also such a situation here. No? K equals 7 gives a really big gap, and then for k equals 8, it kind of drops off. No? And you can find further situations here, like for example here at 17 or so. Yep. So the idea is this, and you can think of it a bit like Occam's razor or so, which is a concept from logic. And you can say, okay, if there are different explanations that all kind of make sense, then you should go for the simplest explanation, really. No? And in that sense, the simplest explanation is the lowest number of clusters. Okay. So the concept of the gap statistics is to formulate the k-means model selection as finding the smallest clustering that finds, let's say, notable structure in the data. Yeah? Okay. Good. Let's talk about mean shift briefly. If we check the paper, like there's not a single best idea for the mean shift hyperparameter selection, yeah. But if we check section 3.1 of the paper, and we're also going to do this in our joint meeting, then they're providing a couple of ideas and I think a reasonably good summary of possible approaches how you could do the hyperparameter selection for mean shift. So first possibility, but this is more of a theoretical idea or a theoretical concept. You can say, well, okay, the best hyperparameter, so the best kernel size is the one that optimizes the bias variance trade-off. So do not choose it so small that the bias becomes excessively large, and do not choose it so small that the variance becomes excessively large, and do not choose it so large that the bias becomes excessively large, but choose some middle way. Okay, then there's an interesting remark for univariate inputs. They are referencing a paper, but I didn't dig down in the literature there where you can achieve this. But I didn't check. And I don't expect you to check, obviously. I'm just mentioning it for the sake of completeness. Second possibility, you can use stability of the number of clusters as a criterion, which I find a bit ad hoc, but okay. So you can vary the kernel size and produce different clusterings then. And you can say, okay, then I track how the number of clusters changes over different kernel sizes, and then I choose that kernel size that gives me, for the biggest range, a stable number of clusters. Other possibilities would be something like to set up an explicit objective function. For example, you could say I'm optimizing inter-cluster variability versus intra-cluster variability. This goes a little bit in the direction of linear discriminant analysis, if you recall that from pattern recognition. Or you look at certain clusters, like how isolated are they or so, and set a threshold there. These are also heuristic measures. No? I'm just saying this. Okay. Then 4 is always a valid approach, of course, that you say, okay, like, why am I actually doing this clustering? So very likely there's some form of a downstream application, and you can use the performance or the properties or whatever requirements of that downstream application in order to adjust the parameters of your clustering. I think that is a very generic reply, and that makes sense. And then another point that I think is interesting is that they say, well, okay, what you can also do is that you locally check, like, how dense is my data, or like what is the local structure of my data, and then to locally adapt the kernel size in order to prevent cases like this disconnect that we saw of very isolated points. I also didn't really dig down into the literature there. But they also provide references for that. I mean, these are certainly also possibilities, but there's not this like one calculus or so that you could apply to say, okay, this is my bandwidth selection criterion. Okay, let's talk about the Gaussian mixture models. For the Gaussian mixture models, we argued, well, these are probabilistic models, Bayesian. If we carry this through this argument, then we should say, well, hyperparameter selection should also be probabilistic in that part of that probabilistic framework, which effectively means that we're moving from a situation, I have it here on the left, where we have observations. I took this from Wikipedia, sorry, shamelessly stole it. So we have observations collected into K clusters, and these K clusters are described by means and standard deviations. And the K is something that is given before, for example. No? So we can say, well, let's extend this. So this means K is a random variable. The means and the standard deviations or covariances actually in a multidimensional case. No? These are variables, so they need. So here's no case. Sorry. So they need priors then again, prior distributions, which is here denoted as mu0, lambda, nu, sigma 0. Here we have a prior beta for a Dirichlet distribution, and most likely. So the hyperparameters become variables in a sense that again have priors associated, and we have to find the most plausible, like a distribution of such models, where again we can select the most plausible model from. This is really cool, but as you might recall, already for the fitting of Gaussian mixture models with fixed Ks, we didn't have a closed form solution, but instead went for an iterative expectation maximization algorithm. Now, if we say, yep, let's further extend this, we also want to dynamically choose K, the number of clusters, then we are making the task even more difficult. And it turns out that we need some additional approximations in order to be able to solve this. Yeah? And this is what we're going to talk about in the next weeks. So one direction in which we will look is the so-called variational inference. The idea of variational inference is to approximate an intractable function, like our fitting function for the Gaussian mixture model with variable k, with a simpler tractable function. And what does that mean? So the choice of that simplification introduces inaccuracies, but the solution to that simpler function, this in many cases of variational inference, can be exact, which is actually a nice property. And variational inference has a big competitor conceptually. This is a sampling-based solution. So we're going to talk about Markov chain Monte Carlo sampling. So this approximates an intractable function with a finite number of samples. So the situation is here the other way around. So while the objective function can be exact here for the case of Markov chain Monte Carlo sampling, the sampling procedure typically introduces inaccuracies. So both solutions are approximate solutions, but they approach it from different directions. And I think that's a really interesting situation that we have here. We will talk about this more in the very near future. So far, I say thank you and talk to you soon. Bye-bye.